to recognize a good leaving group. Here we have the reaction Rx, which is substrate, and it is reacting with nucleophile Y minus. We are getting the new product, that is a substitution product Ry, and here X minus is the leaving group. So this Y minus, as it is nucleophile, it will attack here, and X minus, that is the leaving group. Now how to know whether it is a good leaving group? The simple answer is it must be stable, because when it is stable, then only the equilibrium can be shifted from left hand side to right hand side. And in bracket it is mentioned that it must be weak base. Now why it is so, that we will understand in a few minutes. But when we are saying something stable, that means it is actually weak. Or you can say it is equivalent to say that it is non-reactive. So stable, weak, non-reactive, all these are actually saying the same thing. Similarly, when I am saying thing that some stable, some unstable species is there, basically you can say now it is strong, or you can say it is very, very reactive. Okay, so these are the terms that are actually meaning the same thing. So it must be weak, but why weak base, that we will understand after some time. The leaving group can be considered as nucleophile for the reverse reaction. Reverse reaction is where Ry is basically, now it will be substrate, X minus, now it will be the nucleophile, now it can also attack here, Y minus can be removed. So this is the reverse reaction, and in this case X minus will play the role of nucleophile. Forward reaction will be favored if leaving group is weaker base compared to nucleophile. That means here if we compare X minus and Y minus as weak base, X minus must be more weak compared to Y minus, then only forward reaction will be favored. Now if this statement is true, that means equilibrium will be possible when their basicity is comparable. So we can move from left to right or right to left, both possibilities are there. So basicity of the nucleophile and leaving group when comparable, then we can say that equilibrium will be established. Next we will see why we are saying that it must be weak base. So here X minus, if we consider as base, then the corresponding acid, just add one H, it will be HX. And suppose you are dissociating HX, you are getting proton H plus and the conjugate base X minus. So when X minus is very, very stable, then only the dissociation of HX to H plus and X minus, it is facile process. So higher is the basicity of this conjugate base, sorry, I am trying to say stabler this conjugate base or weaker this conjugate base, that means this dissociation is favorable. So these two statements, that stronger is the acid, weaker or stabler is the conjugate base, because then only this left hand side to, we can move from left to right, that is we are getting H plus and X minus, dissociated form of HX. So when stronger is the acid, stabler is the conjugate base, or stronger acid means what? Obviously pKa will be lower. So the relationship of pKa of HX and the corresponding conjugate base, this is the relation, that lower is the pKa of HX, weaker will be or stabler will be X minus. That means in any reaction, if you want to know whether X minus is good leaving group or not, what you have to do? You just have to consider the corresponding acid of it, which is HX, and then what is the pKa? That is, if you have two reactions and if you want to know in which case the reaction will be favorable, so we want to know in which case leaving group is better, then you have to consider the corresponding acid of these two, two leaving group, because we are comparing two reaction, and then check the pKa. So here we have leaving group, suppose three leaving group, I minus, iodide, CH3COO minus, acetate and hydroxy, HO minus. So what we will do, the next step is just consider its acid form, HI, then CH3COOH. So X minus, just move to HX, and HO minus, it is simply water. Now what are the corresponding pKa? Basically here we know hydroiodic acid, that is stronger among these three, then acetic acid, then H2O. That means minimum pKa, that will be for HI, then acetic acid and then water. So these are the pKa values mentioned. So from this you can draw the conclusion that nature of nucleophile, that will be good for I minus, it is moderate leaving group capacity for CH3COO minus acetate group, and acetate ion, and then HO minus, that is actually 4. So this is the order of leaving group capacity for these 3 species: I minus, CH3CO minus, and hydroxy. Fine. Now we will solve one problem from which you can consider it is application of this whatever we have just learned. So this is a question from CSIR-NET, and it is asking that for the following compounds, the correct order of reactivity towards nucleophilic acyl substitution. So here what are the species given? Reactivity towards these substances that are given in the question. The first one is acetyl chloride. Now acetyl chloride, CH3COCl. Then the next species given, methyl acetate. You can consider any option. There are actually total 4 species. So this is methyl acetate. Then we have acetic anhydride, CH3CO, OCO, CH3, and we have one more species which is acetamide, CH3CO, NH2. Now here one thing is common. What point is common? CH3CO part is common, so just Cl, OCH3, then OCOCH3 and NH2. These parts are basically, you can consider it is as if leaving group. So in general we can write the equation as if it is RCOLG, leaving group. Nucleophile is not given. Suppose there is a common nucleophile and you are doing this reaction, RCONU and LG is removed. So if we want to know which LG is better, that means that will be the most reactive. So suppose if you consider option 1, it is saying that acetamide is that is order of reactivity is maximum. That means the corresponding leaving group NH2, that will be better leaving group. So we just have to choose in which case the leaving group is better. So next what we will do, we will write the leaving group which is Cl minus, methoxy, then we have acetate, and we have amide. Next point, we will write the corresponding acid. Okay, so it is HCl, this is basically methanol, this is acetic acid, and this is, just add one hydrogen, ammonia. Now if you consider the acidity of these 4 species, maximum acidic is HCl, after that it is acetic acid, then it is methanol. So this is the order of acidity I am writing, and we know when acidity order is so, then the leaving group, corresponding leaving group, that will be stable. So here Cl minus, that will be maximum stable. Then we have, so this is the stability order of leaving group. So when this is the stability order of leaving group, that means this is also the order of reactivity of these substances given. So here maximum reactivity that you can expect for CH3COCl, because here Cl minus is the stable leaving group. Now acetyl chloride, that is present here and here, option 2 and option 4. Next will be for acetic anhydride. After Cl minus, CH3COO minus, and the corresponding substrate is this one. Now after acetyl chloride, the next one, acetic anhydride. Now that is also present in option 2 and option 4. After that what you have? Methoxy, that means CH3COOCH3, methyl acetate. So after acetic anhydride, we have methyl acetate only in option 2. So this should be the correct option. And at last there is acetamide. So option 2 is the correct option. So in this way, from leaving group, whether it is good leaving group or bad leaving group, from this order we can solve this question. Okay. So I will come with some more question. Today we have only this. Thank you for listening.